Good morning, everybody. Welcome back to Calc 3. Our plan for today is we're going to start by finishing Standard 6. And if we have time towards the end of class, we will start talking a little bit about Standard 7. We'll start talking about limits, getting some actual calculus material in this Calc 3 course. As far as homework goes, on Friday we are going to have a quiz on Standard 6. As far as office hours go, we've got office hour this afternoon from 2 to 3. Tomorrow morning, I'm going to have to cut my morning office hour a little bit short due to a meeting, so 10:30 to 11, I'll be persuaded to go past 11 a little bit. And also tomorrow from 1 to 2. Got a big pile of things to pass back, including quizzes and exams. So go ahead and do that. Katie. Tim. Avery. Lindsay. Sarah. Hannah. Alex. Sean. What's for different use of them? Why? That's what students like. I always have a mental image in my head that they're in one part of the room. Jerry. Luke. Dog. Wits. John. Emily. Jack McCoy. Benny. Olivia. Will. Corey. Jacob. Jack Smith. Jackson. Holly. Brianna. Also, someone turned in a Standard 5 quiz with no name. Come see me after class if that's you. If you took the Standard 5 quiz and didn't get one back just now. Okay, general comments. This is the first exam. I haven't updated Blackboard yet, so the totals on Blackboard do not match what you've actually earned as of this exam. I'll probably update Blackboard at some point this weekend with your full mastery totals. I feel like the exam went pretty well overall. I know some of you probably didn't do as well as you would have liked. If that is you, here's what I encourage you to do. First of all, do not despair. Every standard, 1 through 5, will appear on every other exam for the rest of the semester. So 3 more midterms and a final. Meaning, if you didn't do well this time, you still have plenty of opportunity to still get those masteries later on. Plus, you can always come and retest outside of class. If you didn't do so well, and you haven't been taking retests, I encourage you to consider doing so outside of class. Just kind of an easy way, once per week, you can earn a potential mastery. Yeah, and if you feel like you didn't do well because you kind of weren't prepared for what to expect from an exam, if you'd like, I encourage you to come set up an appointment with me to talk to me outside of class, and I could help give you some tips on ways that you can improve for next time. Always happy to talk about those sorts of things. Any questions or comments on any of the stuff I just passed back? Okay, second exam I think is after standard 10, I'm going to say. So, we've been talking about standard 6, multivariate. Oh, before I forget, did you know there are 10 kinds of people in this world? Those who understand binary and those who don't. Okay, so today I want to focus on going back to talking about multivariable functions, kind of the last part of standard 6. And in particular, I want to focus on talking about how do we graph functions by hand today. So first of all, given a function f going from R2 to R to R, it's going to be a graph that takes in two-dimensional vectors as inputs and spits out a single dimension as outputs. And these are, other than parametric graphs, which are ones that have just single and scalar inputs of t, these are going to be the types of graphs that we are used to looking at. So as a quick review, in Calc 1, whenever you talk about graphing functions, we typically have one variable as a function of another variable. Do we usually write out y as being a function of x, or x as being a function of y in Calc 1? Okay.
Y is a function of x.
Yeah, usually we're going to have x as being our independent variable, and y as being our dependent variable. By which I mean, if you're given a function like f of x equals x squared, we're setting y to be the output and x to be the input. And so for y equals x squared, you can plug in anything you want for x. Any real number goes in for x, but once you plug in a number for x into your independent variable, your y value is determined based off of that. So if you were to plug in x equals 3, you're going to get an output of 9 every time. So x here is the independent variable and y is the dependent variable. When we graph functions from R2 to R, we're usually going to have a similar sort of thing going on where we have independent and dependent variables. The catch this time is that for these sorts of functions, we're going to have two independent variables, x and y, and z is typically going to be our dependent variable. Meaning, typically, for functions from R2 to R, we're going to be writing z is equal to some function in terms of x and y. So let's do an example. Let's say we wanted to look at the function f of x comma y is equal to x plus y. When we graph this function, what this function is going to look like is, graphically, is something in 3 dimensions where our outputs to the function are going to correspond to z values, and our inputs into the function, the independent variables, are going to be both x and y. They're independent in the sense that x and y don't have to have any relationship to each other. They could be the same. We could plug in like f of 1 comma 1, or they could be completely different. We could plug in f of 3 comma negative 5 trillion into this function if we really wanted to. So let's look at this equation. We're going to set f of x comma y to be equal to x plus y, which is the same as saying we want to graph all points whose z-coordinate is equal to the x-coordinate plus the y-coordinate. What does this graph look like? Can we talk about what does the set of points look like that's going to satisfy this equation?
Is it kind of going to be a So I'm going to be exactly how this flipped fault, but it would kind of be like a bowl coming to 0 and then like expanding outward.
It's not necessarily going to be a bowl-like shape. That'll come later today.
It's kind of like a wave that's really that's like high on the positive x, positive y, and it hits 0 and make the x negative y and
It's going to be something, yeah, that sort of comes in and hits the xy plane. I'll give you a hint. I'm going to rewrite this equation like this. Does this look like any type of geometric thingamajig that we've talked about how to look at algebraically and graphically before? Yeah?
It looks like a vector.
It looks like a vector. How so?
We have it looks like the standard form of the plane, which was ax plus by plus cz equals the constant d.
Yeah, that's exactly right. This right here is actually giving us the equation for a plane. And in particular, I think reading off this equation for the plane, we can actually tell some information about the plane. In particular, what would be a vector that's normal to this plane? If we read this off in the ax plus by plus cz equals d sort of way. It's a very similar question on the exam, and I know several of you were able to find it. How can we find the normal vector to this plane just from looking at this equation right here? X plus y minus z equals 0. Okay.
Is it 1, 1?
Yeah, exactly. It's just the normal vector is just going to be peeling. I don't want to circle it because that looks like a 0. It's just going to be looking at all of the coefficients on the terms in our standard equation here. So we get a normal vector of 1, comma 1, comma negative 1, because this is the same as 1x plus 1y plus negative 1z equals 0. Can anybody give me the coordinates of a point that happens to be on this plane? I will. 1, 1, negative 2. Correct. 0, comma 0, comma 0 is in fact the point on this plane. Actually 1, 1, negative 2 doesn't work. If you did 1, 1, positive 2, that would.
Oh, it's minus c,
Okay, because it's minus c. I'm going to go with 0, 0, 0, Joe, just to make it easier to graph. Just having the origin be a point on the plane. But 1, 1, 2 also totally would work. And right off the bat, we should be able to try and sketch a graph of the plane with a normal vector of 1, 1, negative 1, and it happens to pass through the origin. Because the origin here can be our p naught, since it happens to satisfy the equation, x plus y minus z equals 0. And then if we have a vector, 1, 1, negative 1, that we draw as a displacement vector from p naught, we could go 1 in the x, 1 in the y, negative 1 in the z, and have this be our normal vector. And then we could just try and draw what does the plane look like that happens to pass through the point p naught and that also happens to have a normal vector of n. If we draw that out, it's going to be a plane that looks a little something like that, I think. That happens to pass through the origin, through the point 0, 0, 0, and our normal vector is going to be perpendicular to this plane, meaning it's going to be sticking straight out of it. And kind of coming out of the board a little bit, to the right a little bit, and down a little bit. So the normal vector is pointing like this way, and so our plane is just going to be perpendicular to that. And, wakey wakey, if we actually look at a graph of this plane, what we're going to end up seeing is if we graph the function z equals f of xy, and if we were to graph z equals x plus y, that's precisely the plane we would get. Dr. Gersel, it looks like a hexagon. It's a plane. The reason why it's getting cut off as a hexagon is because it's only going up to the edges of this box. But really, this extends out forever and to the left and right, up and down from here. So I have a question for you. How accurate was our graph? Was this picture and looking like that plane? Don't worry, I already have very little self-confidence when it comes to my artistic skills.
Not very accurate.
Not very accurate. Ouch. But I agree. Yeah. And in general, when you graph a two-dimensional function, like y equals a function of x, graphing something like f of x equals x squared, that's pretty easy to do on like a two-dimensional surface because, well, you just do it. You just draw it out so it looks like the graph. The problem in trying to draw a graph of a three-dimensional function on a two-dimensional surface is that you're probably not going to be able to do a very good job of it. Even with, I know at least a couple of you said you're interested in art in here. Even the art students in the class will probably struggle to do this unless they spend a very long time on trying to actually draw out the plane. And this is just a simple function as f of x comma y is equal to x plus y. Imagine if we wanted to graph something along the lines of, say, I don't know, f of x comma y equals the absolute value of x minus y. Which we're going to be looking at in a second. Moral of the story is, we're only going to be talking about how to graph these sorts of functions for just today, because nowadays, if you ask any mathematician, what does a graph of this three-dimensional function end up looking like? They're going to plug it into a computer and say, here's the image on the screen. Because trying to graph three-dimensional things by hand is hard and inaccurate, usually. So we're not going to do much of it over the course of this semester. Usually if you ask me to graph something, I'm just going to pull up Matplotlib and say, here's a picture. That being said, multivariable calculus existed for hundreds of years before computers. And so for a very long time, mathematicians actually couldn't just go to Calc-Plot3D. They had to graph these things by hand. And so I do think it's worth kind of looking at, at what did mathematicians have to do in the past when they were asked to sort of graph out these functions by hand. And so kind of today's class is going to be focused on, for something like a plane, we know how to graph that because we know how to rewrite this, find the normal vector, find a point on the plane, and just draw a picture of that. We know how to graph planes. That's not so bad. That's like in Calc 1, just drawing a straight line. It's going to be challenging, though, graphing things like this that are not just going to be planes. And so I'm going to spend the rest of today talking about techniques you can use to try and draw out, how would mathematicians in the past have tried to draw this out by hand. I'm just going to draw a big axis that we're going to refer back, but we're not going to graph anything on it just yet. And the way mathematicians would do this is through the use of something called contour curves and level curves to the function. So first of all, given a function, any function f that's going to go from R2 to R, meaning that's going to take in x and y coordinates as inputs, as the independent variables, and is going to spit out a z coordinate as the dependent variable. we can talk about two things associated with f. We can talk about the level curve, at height c of the function f. And what we mean by the level curve of the function is it's going to be the set of points x comma y in R2 that are going to satisfy that f of x comma y is equal to a constant value c. And another thing that's going to go along with the level curve is something called the contour curve to a function at a particular height, in which the contour curve at height c of the function f is going to be a set of points in R3, x comma y comma z in R3, where f of x comma y is equal to c, and c is equal to the z coordinate of all the points that we're going to be looking at. And these two tools, level curves and contour curves, are going to be a way that's going to allow us to help draw a graph of a function from R2 to R by splitting it up into smaller pieces. So let's do an example of what one of that might look like. So to start off, we're going to be looking at f of xy is absolute value of x minus y. And I'm going to be looking at three separate values of c for which we're going to find level curves and contour curves. We're going to be looking at c equals 0, c equals 2, and c equals negative 2. So first of all, let's see if we can sketch what does the level curve look like at c equals 0. So by definition, the level curve is just going to be a set of points in R2. So it's going to be a set of points with just x and y coordinates that if we were to plug in f of x comma y, we would end up getting 0 as the output. 0 because we're looking at the level curve at height c equals 0. So if we plug in our equation for f of xy, we end up with a set of points where the absolute value of x minus y we're going to set to be equal to 0. Can anybody tell me what does the set of points look like in the xy plane satisfying this equation? Doc?
Wouldn't it just be y equals the absolute value of x?
Yeah, if we add y to both sides, we'll just get y equals the absolute value of x for this equation. Sorry, you were about to say something else?
And yeah, so then just kind of a v the graph.
It's just going to give us a V shape. Boom. So in other words, the set of points in the xy plane that happen to map to a z coordinate of 0 underneath this function is just going to be this V shape corresponding to y equals the absolute value of x. As long as y is equal to the absolute value of x, then when we plug in that x and that y into the function, it's going to give us an output of 0. So now that we know what the level curve looks like, we can look at the contour curve, and that's going to tell us how we can graph part of our function. So remember, for our contour curve, we're going to need points x comma y comma z, and we want those points to satisfy that f of xy is equal to c, f of xy is 0, meaning we need y is equal to the absolute value of x, and we want points in R3 whose z-coordinate is equal to our value of c. So in this case, our z-coordinate is 0. And so if we graph the set of all points in R3 whose z-coordinate is 0 and whose y-coordinate is equal to the absolute value of the x-coordinate, what we're going to get for our contour curve, this will be x, this will be y, this will be z, is basically just a set of points whose at z equals 0, so it's going to lie flat in the xy plane, and if y is equal to the absolute value of x, what we're going to get is going to be a curve that looks something like this. Should have bought some colored chalk today. So I'll make it extra bold so you can kind of see it a little bit more clearly. That's going to be the set of all the points in the xy plane whose y-coordinate, meaning at z equals 0, whose y-coordinate is equal to the absolute value of the x-coordinate. So all that I really did was I took our level curve and I kind of plopped it into 3 dimensions. Just took this 2-dimensional level curve in the xy plane and graphed it in 3 space, all at a z-coordinate of 0. So picture basically this as being a V shape that kind of spreads on either side of the positive y-axis. Dr. Gerstle, what's the point of this? The point of this is that once we know what our contour curve looks like at, say, c equals 0, this tells us something about how the actual function, f of xy equals absolute value of x minus y, is going to behave there. Because now we can kind of pick up this contour curve at z equals 0 and make that part of our graph. Because we know that our graph of this, if we were to only look at the points on this graph with a z-coordinate of 0, this is what we would get. All of these points satisfying y equals the absolute value of x at a z-coordinate of 0, are going to be points on the graph of the 3-dimensional surface we'll get when we actually graph out f of xy equals absolute value of x minus y. Think of it as a cross-section of the graph. The whole cross-section is an entire surface, but if we just sliced that surface at z equals 0, sliced it into like horizontally, this is the piece that we would get there. And ultimately, our goal for looking at how do you graph this whole surface is you graph a bunch of different contour curves at different values of c, and then once you have a bunch of different contour curves, you sort of connect them, so to speak, in order to get a graph of what the actual surface is going to look like. If we slice that graph open at c equals 0, we're going to get this flying V shape. Let me stop for a second and just ask, what questions you all have so far about how we found either the level curve or the contour curve, or what that curve has to do with the function as a whole? Yeah, Emily?
Can you walk through how you have the contour curve again? Like, why is z equals 0?
The reason why we plugged it in at z equals 0 is because I specifically was looking for the contour curve at c equals 0. If we were to look at, in a second, we're going to look at a couple other contour curves for the same plot at c equals 2 and negative 2. And when we do those, instead of setting f of xy equal to 0, we're going to set them equal to 2 or negative 2. And then the z-coordinate will be set equal to whatever our c value is. And that'll tell us, and what that'll tell us is that different values of z, so at different cross sections of your surface, what is it going to look like? What is the graph going to look like?
So with that, why does the level curve give us a 2 first complex and the contour curve give us
It's because that's just how they're defined. The level curve is specifically designed to be a set of things only in R2, whereas the contour curve is specifically designed to be, or specifically defined to be a set of points in R3.
Okay, so then with the level curve being on two, it still means that x and y are both independent, right?
Independent as far as f of xy is concerned, correct. But they suddenly become dependent on each other if you want f of xy to be equal to a specific number. Once you set like an equation like this, we want f of xy to have to be equal to 0, then all of a sudden you get something where y and x do, that you can rewrite where y does depend on x. But without specifying, I want to set f of xy equal to 0 or 3 or whatever, then they're independent of each other, because as far as just plugging in numbers into this function is concerned, we can plug in whatever we want for x and whatever we want for y, and they don't have to have any special relationship to give us a point on our graph. Let's look at a couple other, let's find a couple other contour curves and level curves, just to see what they look like. And then once we find other contour curves, we'll continue adding them to our bigger graph that we're trying to build up. Let's do it c equals 2 next. I like to start with finding the level curve because to me, finding the level curve helps me to visualize what the contour curve is going to look like. Just graphing it in 2 dimensions before trying to put it in 3 dimensions. So if we start by trying to look at our level curve, at c equals 2, we're going to have to set f of xy to be equal to a positive 2, which if we plug in our expression for f of xy, we'll get absolute value of x minus y is 2, or in other words, y is equal to the absolute value of x minus 2. Because if we add y to both sides and subtract 2 from both sides, we'll get y equals absolute value of x minus 2. And how does the graph of y equals the absolute value of x minus 2 look different from the graph of just y equals the absolute value of x? Oops.
Isn't it just shifted 2 down, negative 2 down on the y-axis?
Yeah, it's the same graph, but just shifted 2 units down. So if we graph that, 1, 2, here's going to be our new level curve. At c equals positive 2, our level curve is going to be the absolute value of x function shifted down by 2 units. And the reason we have a negative 2 here is because we have to subtract 2 from both sides and add y to both sides in order to get y by itself. What's that? How embarrassing. So let's look at the contour curve now. For our contour curve, we're looking at a set of points, x comma y comma z, where f of x comma y is equal to 2, the 2 just coming from looking at the curve at c equals 2, and we need that our z-coordinate is equal to 2. So in other words, we're looking at points where the y-coordinate is equal to the absolute value of the x-coordinate minus 2, and the z-coordinate is just set to be a positive 2. Which if we draw that out, here's our x, here's our y, here's our z. We're going to need to do something a little bit tricky. It's not just as simple as picking up the absolute value function and moving it up 2 units this time. Because now, our level curve, y equals absolute value of x minus 2, is shifted to have a vertex at an x 0.0 and a y-coordinate of -2. If we do the same thing draw the same thing in our contour curve, we're going to get that we have to go 2 in the negative y direction. And now our vertex is going to be all the way up here, and then go out this way. So that this time, our vertex for the absolute value isn't just going to be on the z-axis. It's going to be 2 units to the left of the z-axis at the point 0, -2, +2. Where the vertex has an x and y coordinates of 0 and -2, since those are the x and y coordinates of the vertex in our level curve. And the fact that they have a z coordinate of +2 comes from the fact that we're drawing this at a height of c equals 2. Meaning all the points on our contour curve here have to satisfy that their z coordinate is a +2. Which, now, we can go over and actually add this contour curve to the plot, or to the graph of f of xy that we've been building up. And if we do that, we'll get this point here. And that's going to give us another contour curve to our function. It's going to be the contour curve at c equals +2 this time. So what we just did was we took a different cross section, we sliced our graph horizontally, this time at a different height, at a height of 2 instead of at 0. And if we sliced it at a height of 2, this is the picture that we end up getting. Meaning we still have the same sort of V shape that we did down at c equals 0, but this time it shifted 2 units to the left as we've gone up. Our V shape has kind of gone up and to the left here, going from a height of 0 to a height of 2. Let's graph one more contour curve, and then we'll talk about how you sort of connect them all up. Last one I want to look at is going to be at a height of -2. Which, when we graph that for a level curve, we're going to be looking at points where f of xy is equal to -2, which means absolute value of x minus y is -2, which when we solve for y will give us y equal to the absolute value of x plus 2 this time, because we add 2 to both sides and add y to both sides, we'll get this equation. And so our level curve at a height of -2 is going to be the absolute value function shifted upwards by 2 units. And then with our contour curve, we want the set of all points x, y, z satisfying f of x comma y is equal to -2 and z is equal to -2, which is the same as saying y is equal to the absolute value of x plus 2, comma, z is equal to -2. Or again, this equation right here is just the point satisfying f of xy is -2. And if we graph this in 3 dimensions, the point satisfying this equation, y equals absolute value of x plus 2, and this equation, z equals -2, what we're going to get is we're going to get an absolute value looking V shape down at z equals -2. But this time, where's our vertex going to be located at? Is it going to be to the right of the z-axis or to the left of the z-axis in this case? If we're basically trying to pick up this function, rotating it and transplanting it into three-dimensional space. It's going to be to the right this time because we're going 2 units. It's starting 2 units in the positive y direction. So here, our contour curve, same V shape as before, but shifted down and to the right 2 units. And when we graph that out over here, we're going to get a plot that looks something like this for a contour curve. And this will be the contour curve at C is equal to -2. If we wanted to, we could keep going and keep drawing more contour curves until we're sick to death of it. I'm not going to do that, though. So what we're going to do instead is we're going to connect them all up and say, once we kind of have a sense of the contour curves, we can sort of see that as our function gets higher, we're taking a V shape and moving it to the left as we go up. And as we go down, our V shape's going to go to the right. And so when we combine those, we can sort of connect the dots of the vertices, so to speak. And what ends up happening is we sort of get a V shape. Like a V shape that looks like this, going from top left down to bottom right. We have a V shape that's at 2 is over here, at 0 it's here, at -2 it's down here, and so our graph theoretically should look like a sort of book-like shape, a book that's kind of opening up and to the left, or down and to the right. Let's compare that to the actual graph, see how well that shapes up. Here's an actual graph of what our function z equals absolute value of x minus y is going to look like. It is indeed a V shape that's opening up and to the left or down and to the right. Jerry, I'll let you be the judge again because I can't stand to ask anyone else. Does what I drew out by hand here look like a pretty good graph of what this book-like V shape is?
It was a good effort.
It was a good effort. Dr. Gerstle gets an A for effort. That's a very diplomatic way of saying no, it doesn't really look like it. And I agree. But now that we have this up on the screen, let's look at the contours. And if you click on this red button right here, I don't know what this red picture is supposed to be, but if you click on it, let's say, oops, I accidentally clicked out of it. I want to start at -2 as my first contour level. Let's say we want to graph, 30 of them, and they can be 0.2 apart. You can actually see each of the individual contour plots graphed out on this surface. Let me get a good angle here. It's hard to get at a good angle sometimes. I need to. Each one of these red lines is corresponding to a different contour curve on the graph of this function. So here, let's do it with fewer. It's not used quite so many. Let's say we start at -2. We'll make them 1 unit apart. And then we'll only have 6 of them. Here's our level curves, by the way. It'll even tell you, here's the level curve at c equals -2. Level curve at c equals -1. Oops. Do-do-do. This is, go away screen. Do I get rid of this? Yeah. Oh, sit. Hoop. Hoop. Hop. What did I just do? Technical difficulties. Hold on a second. I don't use this too often, so. Alright. Show. Whatever. In every direction, but sure. Okay. Cancel. I'm looking at the wrong one. That's why this is weird. Here we go. Here's our level curves at -2, -1, 0, 1, 2, etc. You can actually see all of them graphed out here. And then when we click on it in 3 dimensions, we can actually see 6 different contour curves. And so the process mathematicians used to go through to have to graph these surfaces is they do something like try and really painstakingly graph out something like 6, maybe 6 different contour curves to the function, and then sort of try and connect the contour curve so that it has a nice continuous shape to it. Sort of like what's going on here. Once we have just the contour curves without the plot itself, show the contours on the surface, hide the surface. Let's do that. You can't see the actual surface just from looking at a few different contour plots, but you could probably see how you could get a sense of what the surface is going to look like if you were to connect together what all of these different contour plots are. By connecting the contour plot, so to speak, you actually get what the surface ends up looking like. In this case, sort of a book shape. I'm going to stop for a second and just see what questions do you have about this process. Ideally, you make really nice looking contour plots and you get a beautiful graph like this. In practice, if you have the artistic skill of Dr. Gerstel, or at least according to Jerry, you end up with something that's a mess that maybe it sort of could look like that. Hey, I can see how there's some V's involved, but blah, 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 not the best looking thing. And so that's why graphing is not going to be a major thing we do going forward outside of Standard 6. But I do think it's important for you to kind of see the process to get a sense of what would you do if you had to graph out these sorts of surfaces by hand. Any questions? In that case, I have an example that I would like all of you to work on. If you flip to the next page in the packet, it's going to be the last page of this packet, actually. I'm going to give you a function and 4 different values of c. What I would like for you all to do, and I encourage you to work with your neighbors, talk to the people sitting around you to do this, I want you to find a graph of what the function f of x comma y equals 4 minus x squared minus y squared looks like. And to do it, I want you to find contour curves at c equals -5, 0, 3, and 4. So your goal, sketch a graph of this function using contour/level curves at these 4 values of c. And here's my hint. When you're trying to graph each one of the level curves, try and graph them all out by writing them in the form x squared plus y squared is equal to something. And as a hint, how would we graph x squared plus y squared equals 16 as an example?
The circle with the radius.
Yeah, this would be the circle of radius equal to the square root of 16, which is 4, about the origin. And I think what should end up happening is all of your level curves and contour curves are going to look like circles. Go ahead, take a few minutes and see if you can use contour and level curves to graph out this function right here with those 4 values of c. As always, ask for help from me. Talk to your neighbors, see if they agree with what you're doing, and we'll reconvene in a few minutes. Because the circles do not, the radii do not. Once you feel like you have contour or level curves that you're happy with for all 4 of these values of c, see what happens if you try and combine them all into a single graph. Don't worry about trying to make your graphs look picture perfect unless you have confidence in your abilities. What I'd rather you do is to have a good general sense of what does the surface, overall surface, end up looking like, even if it's not completely to scale. And if you feel like you finish, I have a challenge for you. Only if you feel like you've done the rest of it. My challenge, at C equals a positive 6, what does the level curve look like in the contour curve? So walk around the room. I am jealous of how much better looking your graphs are in general than mine. Once you feel like you have something, I encourage you to maybe turn to the person sitting next to you or around you and see if they agree with see if they have the same thoughts that you do. Okay, so you all are making some really good progress. Sorry to have to kind of cut you off short here, but I want to make sure we have time to talk through this example in the last few minutes of class. If we were to look at C equals negative 5, meaning we're looking at 4 minus x squared minus y squared equals negative 5. If we wanted a level curve, would anybody like to share with me what their level curve at negative 5 looked like?
Circle radius 3.
Yeah, if we add 5 and x squared and y squared to both sides, this is the same as saying x squared plus y squared equals 9, which is the same as 3 squared, which if we graph that out, is just going to be a circle of radius 3 centered at the origin. Which if we kind of plopped in as a contour plot into this graph, we went down to a height of negative 5, we would end up with a graph of a circle of radius 3 centered along the z-axis. Which is going to look something like that. I'm not going to try and draw it to scale to be exactly 3 units, but yeah, that's about what it would look like. How about at c equals 0? We take 4 minus x squared minus y squared equals 0. What's that going to look like as a level curve? No? Yeah, because this is the same as x squared plus y squared equals 4, which will be a circle radius 2. And if we go in and graph that out, at a height of 0, we'll have a slightly smaller circle going on. At c equals 3, we'll have 4 minus x squared minus y squared equals 3, which is the same as x squared plus y squared equals 1. And what does the graph of x squared plus y squared equals 1 look like? Oh, it's going to be a circle of radius 1. This is the unit circle. Even smaller circle. So as we move upwards along the z-axis, as our contour curves go to higher and higher values of c, we're just getting circles around, centered at the origin, that are getting smaller and smaller. So at a height of 3, 1, 2, 3, we'll have a little bitty circle. And finally, at c equals 4, we're going to have 4 minus x squared minus y squared equals 4, which will give us x squared plus y squared equals 0. What is the graph of x squared plus y squared equals 0 going to look like? Okay. Just the point at the origin, because the only point in R2 whose x coordinate squared plus y coordinate squared is 0 is just the origin itself. So here in our graph at z equals 4, our cross section is just going to be a single point on the z-axis. By the way, I asked you as a challenge question to think about what goes on at c equals 6. At c equals 6, we'll get 4 minus x squared minus y squared is 6, which is the same as x squared minus y squared equals negative 2. What's going to be on the graph of x squared, plus y squared? What's going to be on the graph of x squared plus y squared is equal to negative 2? That does not exist. No matter what you plug in for x and y, x squared plus y squared can never be negative, which basically means the contour curve is empty. There's no points on the graph of this function at a z that has a z value of 6. 4 is as high as it's going to get, in fact. And now, if we connect them all, what's the shape going to look like that we sort of end up getting here? Anybody want to describe what that looks like? Eric? A Christmas tree? A little bit. It's a very smooth Christmas tree. The branches are all kind of perfectly lined up with each other. I had someone in my 8 o'clock class, or 8:45 class say it looked like the top of a rocket ship, which I kind of liked. I think this one actually is a little bit. Derry, I'll let you be the judge in the end. If we pull this back up and take a look at the actual graph. Go away. You end up getting this. I think it's because I'm trying to tap that. And we end up with a surface that looks like this, which is indeed sort of like a neon Christmas tree. Christmas tree after you put all the lights up on it. Weird ways. Let's change the color a little bit. There we go. A little easier to see. And our contour plots are in fact all circles except for a point at 4 and nothing above z equals 4. You didn't see that. So Jerry, did I finally do an okay job?
Pretty accurate, yeah.
Thank you. Yeah, this one's a little bit easier because it's just circles instead of V shapes moving through space. So that's it for Standard 6. If I ask you something along these lines on a quiz, it'd probably be something like, here's a relatively straightforward function. Use contour plots to tell me to sketch a graph of what this might approximately look like. And on Friday, we will then jump into Standard 7 and start talking about limits. Some of the actual calculus stuff that you might remember from Calc 1. If you all have a good rest of your day, I will see you all on Friday. Yeah.
Either way, for standard 3, was there anything? I just wrote that so that I could check it easy instead of doing multiples of 12.
Gotcha. Oh, I see.
That's like easier for me to check it.
Okay.
That's what I meant. I
Okay,
didn't
sorry. I thought you were trying to imply those were the same
no,
vector.
no. I just meant that so I could check that they were full 0. Because they'll both be orthogonal. It'll just be shorter.
Okay, I'll give it to you.
You get what I mean?
Yeah. Let me hold on to this for next time so I have it to look off of. But
Yeah,
Yeah,
I should have
can-
wrote that clearer.
sorry, yeah, I kind of was a little bit confused by what you were
Okay.
writing there. Because sometimes those vectors can be treated the same like a slope vector for a line, but in terms of taking a cross product, they're
Right.
definitely not equal. But I get what you were going for.
Me and Hannah definitely have a meet. We were supposed to leave at 12:15, so just we might have to leave a few minutes early. I'm gonna ask my coach.
Okay, on Friday?
Yeah, Friday.
Okay. Okay, yeah, just yeah, if you could let me know maybe before class or something, or send me an email, that would be great. But that shouldn't be a problem.
It's like the hour.
Take it, I guess, if you ever through on this class. Cool. Going to Notre Dame. But fun.
Yeah.
Oh,
Alright,
because
so
what?
did I only use J just because I didn't explain my reasoning?
Yeah, I really want to. Yeah,
Okay.
here, like, kind of part of this is I always want you to show your work. Like, not applicable. Like, even something like saying does not exist because
Okay.
number of columns here does not equal number of rows there is kind of what I was looking for.
Okay. Can I just tell you why I understand it, or should I have to retake it?
I'm gonna make you retake it just because I don't want to do it at this point. But I think on your next retest you'll be well situated for that one.
I think the S5 quiz might be mine without the name.
Where did I put that? Oh yes, the one I marked as Sean by process of elimination.
Yep, that's me.
I was gonna say I was pretty sure it was yours. I didn't want to call you out before the
Yeah.
class, but yeah,
Alright, thank you.
no problem.
Alright.
That's a good one. You too.